In this video, we're going to learn about how to write rate expressions and learn about order of reaction. So if you go back to our lesson on rate of reaction, you'll remember that sometimes changing the concentration of the reactants can have an impact on the rate of the reaction. However, not all reactions will be affected by the concentration in the same way or at all. So changing the concentration of a reactant could actually have differing impacts on the rate. So changing the concentration may have no impact, or it could cause a proportional change in the rate by proportionally changing the concentration, or it could have a doubling effect. There are lots of different varieties here for how concentration can impact the rate of reaction. So that leads us into something called the order of reaction. The order of reaction is the degree that the concentration affects the rate of reaction. And we say the order of reaction can be zero order, first order, or second order. And once you know the order of reaction for each of your reactants in the reaction, you can then write what is known as the rate expression, which we'll talk about. So if we imagine the reaction W plus X makes Y plus Z, the rate expression would be rate is equal to a small case K times the concentration of reactant W to the power of little a times the concentration of X to the power of little b. So little k is the rate constant, so that would stay the same throughout any reaction. Little a is the order of reaction for the first reactant, and B is the order of reaction for the second reactant. And then if you wanted to find the overall order of reaction, you would add up all the subscripts on your reactants. So if A and B was 1 each, then your overall order of reaction would be 2. So this table is found in your KOGNITY textbook in section 16.1.1. It's table 1, and it shows the relationship between order, concentration, and rate of reaction. So if the order of reaction is 0, you could, if you had this reaction, the rate expression could be K times the concentration of A to the power of 0. So what that means is that rate is independent of A. Any change in the concentration of A doesn't affect the rate of reaction at all. So you could increase it, you could decrease it, it's not going to impact the rate. A first order of reaction would be rate equals K to the power of 1, or rate equals K times the concentration of A. You don't need to write the superscript 1. So what that means is the rate is directly proportional. So if I double the concentration, the rate would be doubled. So it would be proportional. A second order reaction is rate changes, so it would be K times the concentration of A to the power of 2. Rate would change as the square of A. So if the concentration gets tripled, the rate gets increased by a factor of 9. If it gets doubled, it would increase by a factor of 4, and so on. So if you take a look at table 2 in the same section in KOGNITY, it shows you that the units of the rate constant will be different depending on the type of order the reaction is. So just be aware of that. So you can take a look at this table and figure it out. You would figure that out mathematically anyway, but if you want to memorize the 3 different rates and their units for the rate constant, this table would be very handy. So we can find the rate expression experimentally. So if you don't know the rate expression at all, you would start with the initial values and you would determine the rate of reaction. And then, so you would put you'd use a certain concentration of each reactant and then figure out what the rate is. And then you would double the concentration of one reactant. So you'd run the experiment again, doubling the concentration of one, keeping the other one constant. And then you would see how it affects the rate. And then you would repeat that with the other reactant or reactants. So we're going to use this example right here. So OCl minus plus iodide ions, O minus plus chloride ions. And then we'll take a look at a table that shows all of these things interacting with one another and figure out what order each reactant is. So as you can see in the first experiment, we had 2 moles per liter of OCl minus, and we had 4 moles per liter of iodide ions, and the initial rate of reaction was this. So you just do your reaction, calculate the rate. Then in the second experiment, if you notice, so we started with 2 here, now we doubled. So we doubled the concentration of the first reactant. We kept the concentration of the second one the same. But if we look at what happened to the rate, it doubled. So it went from 2 to 4. So we can say then it's increasing proportionally according to the concentration of reactant 1, the first reactant. So the order of reaction for the first one is 1 because it's increasing proportionally. Then we have to take a look and see, okay, where is there a point where we kept this constant but changed this? So if we look at this reaction and we compare it to, here's one where we kept it the same, we halved the concentration of this. So let's see what happened to the rate. So when we halved the concentration of iodide ions, we also halved the rate of reaction. So again, this is proportional, half and half. So this is also a first order reaction. So if we wanted to write that out, we could. So for the first one, when we doubled the concentration of OCl minus and kept the concentration of iodide ions the same, the rate also doubled. Therefore, first order. With respect to the concentration of OCl minus. And then conversely, when we halved the concentration of OCl minus, oh no, sorry, let's fix that. I minus, and kept the concentration of OCl minus the same, the rate halved. So therefore, it's first order with respect to the concentration of iodine. So they're both first order reactions with respect to each of the reactants. So now we can write the rate expression. So rate would be equal to K, we don't know what our rate constant is yet, times the concentration of OCl minus to the power of 1. I'm not going to write the 1 because it's implied if you just write that, and then times I minus. So that's our rate expression. So we can find the overall rate of overall order of reaction as well. Remember, you just add up the subscripts, or superscripts. So remember, they're both first order, so the overall order of reaction is 2. It's second order overall because each were first order. So now that we've found the rate of reaction and with respect to one of the experiments, we can now sub everything in, and we know the order of reaction for each reactant. We can sub in the values and find out the value of K. So I'm going to select the one from the first one. So rate, remember, is equal to K times the concentration of OCl minus times the concentration of the iodide. Now I'm just going to put the numbers in. So we remember in experiment number 1 from that original table, the rate of the reaction was 2.0 times 10 to the power of negative 3. And that was in moles per decimeter cubed per second. So mole decimeter to the negative 3 seconds negative 1 is equal to the concentration of, or equal to K times the concentration of the first one, so 2.0 times 10 to the negative 3 moles per decimeter cubed times 4.0, remember that one was a higher concentration, times 10 to the negative 3 moles per decimeter cubed. So remember, we need to rearrange this to isolate K. So K is equal to the rate divided by the concentration of OCl minus and iodide ions. So I've rearranged the expression, and remember, we're going to cancel out one whole set here because dividing this by this will cancel that one out. So our units are going to be switched around. So our value for K is equal to 2.50 times 10 to the power of 2 moles minus 1 decimeters cubed per second. So now we have our value of K, and that will stay constant throughout any of our reactions at that temperature. So now we can calculate the rate of reaction for the missing parts in the table. So if we go back, we didn't know what this one was or this one was. So now we're going to find for experiment 3. So our concentration for the first one is 6.0 times 10 to the negative 3. For our second one is 4.0 times 10 to the negative 3. We need to know this value here. So we're going to go back and solve that. So remember, rate is equal to K times the concentration of OCl minus times the concentration of I minus. Now we're just going to plug our values in. So we have 2.50 times 10 to the power of 2 times 6.0 times 10 to the negative 3. That was the concentration of the first reactant, times 4.0 times 10 to the negative 3. That all computes out to be 6.0 times 10 to the negative 3 moles per decimeter cubed per second. That's our rate of reaction for experiment 3. So now we're going to go back and figure out the rate of reaction for experiment number 5. So 5, we had 2.0 times 10 to the negative 3 moles per liter, or moles per decimeter cubed, for the first reactant, and then 1.0 times 10 to the negative 3 for the second one. So now we'll solve that one. So rate is equal to, we'll put the rate constant in, 2.5 times 10 to the power of 2 times 2.0 times 10 to the negative 3 times 1.0 times 10 to the negative 3. So our rate is equal to, this is our slowest one, 5.0 times 10 to the negative 4 moles per decimeter cubed per second. So we can find the order of reaction for reactants if we look at experimentally and like calculate the rate that way. We can also use them to find the order of reaction using a concentration time graph. So concentration time graphs will have specific shapes for the different orders of reaction. So you plot concentration on the y-axis right here and time on the x-axis. So a zero order reaction would be a straight line, so it would be a linear relationship. A first order reaction would be an exponential curve, and then a second order reaction would be a quadratic curve. So if you were interested in doing to determine the order of reaction that way, you could do a whole bunch of reactions with the different concentration and plot that over time, and then see the shape of the curve and infer that way. You can also plot concentration rate graphs. So in this case, concentration would be on the x-axis and the rate would be on the y-axis. So remember, you'll have to pay attention if you're presented a question. Is it a concentration time graph or is it a concentration rate graph? Because you will see different shapes based on those two. So if it's concentration versus rate, so rate on the y and concentration on the x, a zero order reaction would have a horizontal slope. So it would look like so. If it's the concentration rate graph is a linear directly proportional, that's a first order reaction. And if it is a curve, it's a second order reaction. So again, you can recognize the order of reaction with respect to a reactant based on their concentration rate or their concentration time graphs. So the other thing too, if we take a look at your concentration time, half-life is the time it takes for a reactant to decrease by half. So we often use half-life graphs and equations when we're talking about radioactive decay. So over time, the reactants would dissipate radioactively. So in a first order reaction, the half-life is constant. So if you take a look here, this is a first order reaction. So from 0 to 1 second, it drops by 0.5 or divides in a half. From 1 second to 2 seconds, it drops by a half. And then from 2 to 3, it drops by a half and so on. So you can see this constant decrease in the concentration. So that's a half-life reaction.